Welcome to The Explainer. Today, we are diving into a truly fascinating intellectual journey. We're talking about the story of how machines finally learned to learn. And the crazy part? They didn't do it by following our rigid rules. No, they did it by completely abandoning human logic. So what we're looking at is a massive paradigm shift. It's a story filled with decades of skepticism, incredible persistence, and a quiet scientific revolution that, well, literally reshaped our modern world. Let's get into it. To really understand how we got to the AI we have today, we have to start with a question that totally puzzled computer scientists for decades. If logic was the answer, why did it fail? This question really sets the stakes for a scientific battle that raged over the true nature of intelligence. Because for a very long time, the dominant belief was that to create AI, you just had to program a machine with explicit, logical rules about how the world works. Simple, right? Well, as we're going to see, the real world doesn't exactly play by simple logical rules. Okay, let's dive into this. For decades, you basically had two competing philosophies battling it out over the nature of intelligence. On one side, we have symbolic AI. This was the undisputed heavyweight champion for a long time. It relied on handcrafted feature engineering. That means humans were literally writing out mathematical rules for every single shape, line, or edge a machine might encounter. It was super rigid, and honestly, it quickly reached a point of diminishing returns. On the other side, we have connectionism. This was totally the underdog approach. It's the idea of using artificial neural networks inspired by the human brain. It was data-driven, it was adaptive, but man, it was incredibly computationally heavy. So heavy, actually, that a lot of top scientists just considered it a complete dead end. To see the fatal flaw in symbolic AI, you just have to look at what happens during a simple winter storm. Say, a human engineer writes a perfectly good mathematical rule for a computer to look for a red octagon. Great, but what happens when a winter storm rolls in and covers half of that stop sign in white snow? The human-written logic just instantly breaks, the machine fails, and when you multiply that single point of failure by, every single variable in the real world, nighttime darkness, a sudden glare on the camera lens, maybe a dented bumper, anticipating every single edge case with handcrafted logic, it becomes absolutely impossible. So this transition wasn't exactly a quick victory for the connectionists. If we look back to 1961, we had early neural networks like Rosenblatt's perceptron. But by 1968, heavyweights in the field like Minsky and Papert published this famous critique highlighting the severe limitations of these early models. And that basically sent neural network research into a deep freeze. For decades, researchers, especially folks like Geoffrey Hinton, had to survive in what was known as the AI wilderness. They just kept persisting with this connectionist approach, even when the broader scientific community essentially laughed it off as a total pipe dream. Section 1. Discovering the hidden layers. So the reason for that early AI winter was a major technical roadblock. Those early neural networks lacked what we call hidden layers, which meant they couldn't grasp complex, abstract relationships. They couldn't even detect basic symmetry because they just couldn't put individual pieces of data together to see the bigger picture. The breakthrough to fix this evolved from some early probabilistic concepts, like Boltzmann Machines, into an algorithm called backpropagation. Think of it like a relay race coach. If the team's overall time is slow, a good coach doesn't just yell, "Hey, run faster," right? They trace backward through each runner's performance to pinpoint exactly where the baton pass was sloppy, and then they adjust that specific runner's form. Backpropagation does exactly this, but mathematically. It calculates the error at the output and then propagates that error backward through the hidden layers, tweaking and adjusting the mathematical weights of the connections to improve the network's next guess. And this brilliantly illustrates exactly what we're talking about. In their seminal 1986 paper, Hinton, Rumelhart, and Williams trained a network on a family tree task. Now, nobody went in and programmed the concept of a grandmother or an uncle into the computer. That didn't happen. But by using backpropagation, the hidden units inside the network naturally specialized on their own. They literally built their own internal representations, their own concepts of these relationships, purely from observing the patterns in the data. The machine was genuinely learning from the ground up, rather than just being handed the answers from the top down. Section 2. Surviving the noise. Okay, but figuring out how networks learn was really only half the battle. As computers got better and researchers built larger networks with multiple hidden layers, which is what we now call deep learning, they ran into a massive new hurdle: overfitting. Essentially, these huge networks were like a student who memorizes the exact answers to a practice test, but then totally fails the actual exam. They were just memorizing useless noise in the training data, rather than generalizing the actual underlying patterns. The crucial solution came from a brilliantly counterintuitive paper by Hinton and his team that introduced a concept called dropout. The idea was astonishingly simple. During training, you randomly drop out, or temporarily turn off, a huge chunk of the network's units. We're talking up to 50% of the hidden neurons just turned off. Now, you'd think adding all that noise and basically breaking the network would make it worse, right? But it actually prevents the neurons from relying on brittle co-adaptations. It forces every single part of the network to step up and learn more robust, independent features. And the data was just undeniable. If you look right here, while the error rate of a standard neural network plateaus and stays quite high, a network trained with dropout sees a dramatic reduction in classification error. By repeatedly sampling and training exponentially many of these thinned networks and then averaging them out, they fundamentally solved the overfitting bottleneck. It was a real game changer. Section 3. The AlexNet tipping point. So, all of this persistence, all of these mathematical innovations like backpropagation and dropout, were building toward a singular historical tipping point, a moment that abruptly ended the academic debate between symbolic AI and connectionism forever. At a major computer vision competition called ImageNet back in September 2012, Geoffrey Hinton and two of his students, Alex Grzewski and Ilya Sitskaver, submitted a deep neural network named AlexNet. The runner-up that year, which was still using traditional handcrafted methods, scored an error rate of 26.2%. AlexNet achieved an unprecedented 15.3%. I mean, in a field where progress was usually measured in tiny fractions of a percent over several years, an instant 11-point victory margin was an absolute statistical anomaly. It sent shockwaves through the global tech industry almost overnight. You might be wondering, why did it finally work in 2012? Well, it was really the convergence of three vital streams. First, you had the deep neural network architecture that Hinton's team had patiently refined for years. Second was the raw material, a massive data set of millions of labeled images for the model to actually learn from. And third, the engine. They took NVIDIA graphics cards, which were originally designed just for playing video games, and repurposed that raw parallel compute power to run their massive matrix multiplications. Honestly, without those GPUs, the theoretical math of connectionism would have just stayed stuck in the lab. Section 4. Do machines actually understand? While this massive paradigm shift initially conquered computer vision, today, deep learning is what powers the massive large language models that we all interact with on a daily basis. But that raises a pretty profound philosophical question. Do these machines actually understand what they're processing, or is it just highly advanced pattern recognition without any real meaning? Well, listen to this brilliant analogy from Professor Hinton to understand how these models process language. He says, think of each word as a high-dimensional Lego block that will deform to fit in with the other words. You see, modern AI doesn't translate English into rigid, logical codes. Instead, it turns words into massive vectors of neural activity spanning thousands of dimensions. Imagine deformable Lego blocks, covered in little hands, constantly shaking hands with the other Lego blocks around them to figure out their exact shape based on the context of the sentence. Once they finally form a stable structure, that interaction, that distributed representation, is exactly what understanding looks like in a neural network. It's actually much closer to something organic, like protein folding, than to a logical spreadsheet. But as much as artificial neural networks were inspired by us, they really evolved into something entirely alien. Our biological brains are analog. We learn individually, and when our hardware, our bodies die, our specific neural weights basically die with us. Not to mention, we communicate incredibly inefficiently just by talking. Digital AI, however, is immortal. You can literally have thousands of copies of a model looking at entirely different parts of the internet simultaneously. And because they are digital, they can perfectly share their learned weights with each other, sharing trillions of bits of knowledge instantly across the entire network. Which brings us to our final and really profound realization. Large language models learn using massive amounts of data and trillions of connections via backpropagation. But your brain? Your brain has 100 trillion connections and learns incredibly efficiently from very little data over a relatively short lifetime. Even Hinton himself admits that the brain is almost certainly not using backpropagation. It's doing something else entirely. So, as we look back at the incredible intellectual journey of the deep learning revolution that reshaped our world, it leaves us with an absolutely exhilarating question. If backpropagation isn't how the human brain learns, what incredible algorithm is waiting to be discovered next? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.